development program. Always I wish to inform all the participants that that 1 week of program is going to be very helpful. Suppose if you go through any research articles, maybe of a 6-page or a 10-page, you have to read twice or thrice, at least you need a day. To make it more understandable, you have to study a lot of articles. I hope that it will be more than a week it needs. It means for one paper. To review, at least of say about 10 to 15 articles, you may need a month or more yourself. Suppose if you attend the faculty development programs like this, in a week, you will come across with many papers. I'm sure that this program, it is going to very helpful to everyone. Now, just been introduced. Also, I put a few slides on that to participants. Suppose if you wish to contact me or email or even through mobile or the WhatsApp, you can discuss with me for the topic or the other matters. My area for the research is in the biomechanics, green and the biocomposites. I take the classes for mechanical design and also materials. For undergraduate student also I teach, that is a topic on deformable bodies, that is mechanics of deformable bodies. That is been more favorable subject for me. Likely over 300 international and national journal and conference papers have been done. It is a group activity, and also I organized 5 international conferences, and out of them 4 are indexed in Scopus and published by American Institute of Physics conference proceedings, and also 18 seminars and other STP programs from AICTE, and also a few FDB programs supported by the Institute. About my institute, I'm working this institute last 14 years. What I shown you, it is going to be administrative black. In the west side, you will see the sea. I hope it is only the institute having its own beach, that NITK beach. On the other side, you will see the Western Ghats on the eastern part of it. NITK is well known as a KREC from earlier days. It was founded in 1960, and today is one of institute among 32 NITs in India. It is recognized as Indian Institute of NITs, including IITs and NITs, as a national institute of importance by the government of India from the Act of Parliament. NITK Surathkal is located in the suburban area of Mangalore, is around 300 acres. And also it is in the close proximity of the sea in the western part, and the mid of the campus that national highway passes through, and it serves the major mode of nation to everyone. NITK has 14 departments and approximately 480 faculty members. Some few assistant lecturers or temporary lecturers are also been appointed as per the load conditions. The total student strength comes to around 6,000 in this. Okay, recently that NITK received over 200 crores of research funds from the various agencies, and the faculty, research scholars and MTech scholars, they published a lot of research articles, been around 1,800 in Scopus and also the Web of Science. As per that ranking, institute ranking, that NIRF in 2020. We stand the 13th in the country, and overall in the university it is going to be 33. And the university, that the QS working rank also been a good considerable. Department of Mechanical Engineering is started in 1960 as the institute been started. And it has produced more than 5,000 mechanical engineers till today over the last 1960, almost like 75 years and so on. Department gives the priority to update the mechanical engineering education, primarily the dynamics of technological advances and sustainable development. And the curriculum is revised on a continuous basis. So within the Senate, I hope almost on the yearly basis, looking at the specialized available in the department, we too modify. Department offers the BTech, MTech, and MTech in research and PhD programs. And it caters around 700 BTech students and 160 mechanical students and over 150 PhD regular scholars being abided by. It is thing. Department have a different concept of working. We've been around 50 faculty members. Every faculty members has their own laboratories. The building accommodates around 50 laboratories inside, small laboratories. I am looking after polymer composites lab that facilitates to cast polymer composites and also biocomposites. We have that clean room and also what we call it as a VARTM, vacuum assisted transfusions of the resin system that we have. Even without exposing to environment, we can cast specimens in food. That is, we have an excellent facility. So department has been full-fledged researcher. The facilities may be individual or a project or the institute-wise to cater all the research projects, academic, and also by personal research. We have a lot of facilities inside. Let us come to biomechanics. Biomechanics appears to be a sub-discipline of bioengineering. Bioengineering takes the lot from the physics, lot of other aspects to it. And in general, we deal with the biomechanics, and that is going to be the solids. Biomechanics is a scientific discipline which applies the principles of engineering mechanics or the mechanical engineering to the understanding of the living organisms among plant and animals. What exactly the thing is that mechanical engineering happens to be a part of mechanical engineering that deals with the motion and allied research topics. In general, engineering is an application of science. The science comes from the nature, animals, and living all things all over the earth. If you look at the broad way of understanding the concept of engineering, the science and the nature comes first. The behavior or the movement or the activities of the nature has been understood with lot of observations made by the science people. Therefore, the science deals with the nature and also the existing issues. It is kind of an observations and a concluding. While engineering deals with it is going to be a totally different. Engineering deals with creating something new which not exist. Which uses the science to create something new which is not exist. You take example of machineries or the equipments, they do not exist. In general, if you take engineering, creation of a building, creation of the bridges, the machineries, electronic gadgets, even including laptops or computer, cameras, anything that you take it, these are all manufactured. It means they do not exist. So therefore, engineer deals with the issues to create something new which does not exist. So it has been totally been engineering. My address is going to be likely in quite opposite. The reason is we apply the mechanical engineering science to understand the living tissues in creating something new. It means if you look at very simple gadgets of electronic gadgets or whatever the case, first you have to study what is the requirement. Based on the requirement, you create it. Therefore, exclusively for understanding the behavior, particularly in case of that human studies, a lot of things has to be understood. Then we have to go for the creating that biophysics or bioengineering will go hand by hand. Biophysics or biochemistry being understood by the research, and bioengineering is a practice to create something new according to the demand from participant side. Okay. So biology and medicines are being quite different. They are going to be in the practices. So we deal with bioengineering and mechanical engineering to understand the biological systems. In general, if you look at the definitions of biomechanics, so it is a study of the structure, function, motion of mechanical aspects of mechanical systems. It could be from any level. It may be whole organisms to organs, cells, or cell organelles using the method of mechanics. Study of the entire the structure and the function for a whole organisms. Suppose if you take it in a human body, it will be treated as a gait analysis. It means you will be studying the dynamics of the entire human body at a time. Then will be taken as a gait analysis. Further, all that mechanisms, force analysis, and all dynamic part, if you take it from the human body, that will be called as a sport mechanics. What exactly it entails for. But sometimes we take the few organs, the limbs, or the cells. So these are all comes to the part of engineering. If it is involved with mechanics, definitely it is going to be a biomechanics. What exactly the use of the biomechanics? The application of this mechanics to biological systems to produce some specialized areas. Say, for example, artificial organs, then human limb processes. Artificial organs to make it are a kind of a substitute. Doesn't mean that it is going to be a living part that you are creating. It is going to be another alternative to it. Say, for example, amputate the leg pieces. Say lot of people use Jaipur legs, been very commonly be known as. Say that such artificial limbs that have been to be created. To make such limbs, you have to study the human behavior, mechanics, force analysis, dynamics, and many. So what exactly that meaning is? Medical instrumentation. even to create a lot of medical instrumentation for surviving. It may be what do you call it as temperature measurement to check the fever or kind of thing, blood pressure devices are the monitoring devices, are the glucometers, oximeters, lot of things we come across with the instrumentation part of it, where a lot of electronics is involved in. There also beneath the application of the biomechanics. Nowadays, we find a lot of applications of biomechanics in developing biomaterials. It may be implant or a part of organ or alternative to the organ. So it is going to be very common. It involves the grafting of bones, the bone supports, issue advances, a lot of materials in the dentistry that also been included. Biomaterials also been discussed in creating a lot of safety devices. See, if I considering even industrial, what do you call it as headgears, the helmets, breathing, and a lot of things have been involved in biomechanics and the biomaterial. The cellular mechanics and the tissue engineering nowadays, there are a lot of things is going on with understanding the tissues that has to be derived to satisfy complete the dynamics of the human body. Therefore, the tissue engineering also demands the use of the mechanics in general. The components of biomechanics that is involved, as we thought in mechanical engineering in general, it consists of applying concepts of the mechanical engineering to the medical field. It may one of them or all together. For example, solid mechanics. We thought about strength of materials. See, that very similar to if you apply any external forces on the body deforms. It could be in the form of solid, like maybe a bone or long tissues, cartilages. A lot of things have been involved. When the external force acts on them, how do they behave? What is the admissible and what exactly the mechanics? So the solid mechanics deals with majorly with the bone and hard tissues and the muscles with the forces. It may be forces, or maybe moments, or the torques, or even the body forces itself also being considered. Thermodynamics and the energy conversion between the heat and mechanical, that is going to be in a general. In the case of the biomechanics, the lot of that heat that is developed within the body, decimating it, creating the environment like air conditioners, the reactions of this body. So a lot of things will be studied in this. Again, as fluid mechanics, it is going to be one of the important the features in biomechanics that deals with the fluid dynamics and the forces which act on them. In particularly the circulation of blood, the alternate to the what do you call it as the heart or the tissues, response of the tissues with the varying the blood pressure, a lot of things that has been involved in it, and also inhale and everything, air oxygens and activity of the lungs, and all that air has been discussed with the fluid mechanics. So it is not surprising. One of the best example we quote for the applied mechanics in biomedical engineering comes to this figure. That as Oscar is a runner, he participated in 2011 World Champions in athletes of the region of South Korea. That he is used prosthetic leg blades. So usually the ampute legs support a kind of what do you call it as the prosthetics, like I hope that you might have heard of Jaipur legs, the fit in so that they can walk. We have seen those people simply walk without what do you call it as doing exercise or kind of things. But running in a competition being successfully, so it makes something like blades have been created to such a way that they tackle with all the dynamics of the body into this. So it is going to be a wonderful the example that we quote with the biomechanics. The role of this blade has been going to be very interesting. This blade has to mimic the action of anatomical foot or the ankle joint. Suppose if the another leg that has been used, how it behaves, the same way this blade has to behave. The blade has to store the energy from the body weight and then release it as the runner pushes off. It has to create some additional energy to start with. So it has to do all the activities of the muscles. It is a case of a leg. It could be a leg, the calf muscle or the tension to act it in a spring to start it. Again, it has to deal with. Then motion studies of the limbs like ankle or even the foot for the user has to be taken to. Then design and optimize the prosthetic runner blade based on the strength. Again, it is going to be person to person that it changes. Therefore, the different blades has to be tackled or designed in such a way that looking at that above all other aspects, that has to be designed. The fatigue and life of the prosthetic running blades that has to be taken care of. It should be inexpensive, comfort to wear, aesthetic and safe. You have to look after. It means the design of such a blade takes a lot of effort in analyzing the behavior of the runner, and you have to act upon. And also the selection of a suitable material. It may be alloy or maybe a composite or any material of that has to be designed such a way that all above issues are being tackled with the material. All above challenges demands the role of mechanical engineer in design as well as to manufacture. Not only to design, that has to be manufactured. Therefore, the role of a mechanical engineer in creating medical equipment, it is going to be very, very important. A lot of things are involved in the gait analysis, the relative movement of limbs, the body weight, that energy, where it is being released to the muscles, how do they react? The sorry, the reaction of ground for the participants in the pushing to optimize the what you call it as the processes, and in case of general anything taken to how the force will act on each limb, what are these reactive, and how to make it the best use of it. So it needs the lot of the engineering that is involved in biomechanics. Most of applications of mechanical engineering, in particular to gait analysis, is increasing day by day. Even you take an example of a pair of shoe. Lot of shoes are available from the orthopedic concern, for a sport shoe, for the other. Therefore, nowadays, the sport shoes are totally different from the generally what we use it. The shoes are particularly being designed for a particular sport person to best fit it and to support the activities. Therefore, the gait analysis that studies the complete the human body activity and all the requirement will be based on the entire the body structure of it. So it is being referred to as a Gantt analysis. There are two aspects in general. The one is clinical support, and another is the scientific support. In general, we call it as the clinical front and the technical front. In case of clinical front, all these technicians, medical doctors, the surgeons, all the people are involved in it. So usually those people is involved in practices. These medical practices are generally based on, we call it histological practice. So it means what earlier was the practice, it is continued to that. Whatever the medical prescription has to be given, they had to look back for the history, how other people are previously practiced. Therefore, usually they do not deviate much from the histological practices. For a particular disease, there will be a medicine. For a particular disease, there's a particular surgery or the operation. For a particular case history, the process are being good. So everything is fixed. They will not deviate much from the past. Where the technical front, usually we call the scientific support, it will give you a lot of information to clinical front to practice or support to present practice or to change or to deviate. It means a scientific knowledge developed with the technical front will be given to clinical front. Therefore, that makes the things easier to practice them. So all medical doctors will come in one part. All biomedical and biomechanical engineers will come in the other part of it. So we support scientifically the medical doctors and the practices. But biology in mechanical engineering and life sciences are more becoming exciting and challenging day by day. In particular, developing of new materials for living human beings, like implants for the structural, bony and soft tissues are becoming with the priority. Particularly in the dentistry, we have seen a lot of developments have been occurring from metal to plastics nowadays. A lot of developments are happened in the dentistry too. There are a lot of things that happen in the worldwide in creating new the facilities, medical facilities to the present generation. We have seen the last 40 years effort to replace a heart has been attempted. The cases have been very few, even though it has been very expensive. Some of them have been implanted the artificial heart successfully. So there is the one of the example that have been quoted here. Particularly to tackle that the knee joints, the entire joint have been replaced. In the left side, you will see a joint, how it looks, where in the right side it has been seen that how it has been placed inside of the body. Nowadays, to tackle the knee joint replacement, it may be a part of it or even maybe a total joint replacement. The total joint replacement is been popular compared to part of it. So here what they do is they dissect or cut some portion of the diseased bone, and then they'll fix the aesthetics to this so that they can use it really comfortably in front of it. We will discuss in details in the coming slides. In the artificial human hip joint, in the left side, you will see that implant that has been fixed into the body. It has been practiced over many years, not only the hip joint, but entire that the hip joints that has been replaced with successfully with the artificial that implants and the prosthetics. It has been done well. The one of the very common example to tackle the blockage of the heart tissues, it is a use of the cardiac stent. The material has been developed in such a way that it will be inserted into that blood into the where it has been blocked, and it will be open up. That you will see in the first slide, that has been a stent that has been inserted through the blood vessel that will reaches the heart, and exactly that way place it has to be been opened up, and then you will see how it has been after the angioplasty, how it has been recovered. So the development of the material, the stent use in its life, and how to insert entire the process being developed by the engineers successfully. It is going to be one of a successful the event in the medical field is the use of cardiac stent. Even the wearing the artificial limbs supports, it is going to be fine nowadays, but you will see very simple the prosthetic limbs that has been used compared to more sophisticated artificial limbs, and also the design of shoes that looking at the patient, you have to design or the modify the shoes according to their requirement. So we feel that is design of such things is case to case. It means patient to patient it changes. The structure of the leg, size of the leg, their comfort, the requirement and the needs. Therefore, design of the prosthetic or the shoes is going to be a part of the mechanical engineering. It is not only related to biomedical, also the safety devices, design of helmets. If we feel that it has been readily available, we won't feel that, but a lot of people will insist to go for a good helmet. They had to consider it should be too light, more be comfortable, the safe enough to protect the head. A lot of technique and informative data has been involved in designing the helmet. Also the industrial helmets, you will see that the chest guard, even the industrial glasses that has been used. A lot of activities are being involved in not only designing, also in manufacturing. The dental materials and the processes has come part of it. In the first picture that you will see that a screw at the bottom that will be inserted into the bony part, and the upper cap, it looks like the teeth has been inserted in. Sorry. We have seen the use of the prosthetics are usually being referred to as the dental sets. For old people, the remove of all the teeth and that has been put it in. Nowadays, the trend is to fix the dental art permanently into the mouth. They put the screws all along this four, and this denture have been fixed into this permanently. No need of taking the removal or the frame or kind of discomfort to the patient. That is going to be a part of it, and it is going to be very, very interesting. At the bottom of that picture that you will see that what you call it as the orthodontics make the teeth the corrections, that alignment, and a lot of the practice that has been involved in it. The design of the brackets, the design of that wire, the force that is required to move the teeth safely and medically, a lot of things have been in. So the size wire it is designed in such a way that it exerts a force or a twist so sophisticatedly. So the movement of the tooth has been observed in such a way that the moment of a tooth about the tip is going to be where the cup. It means, for example, if you take this tooth, so because of the force it is applied through this arch wire, it has to see that when the tooth has been moved, only the tooth and the tip and the above has to be shifted, but not the tip of or the root of the teeth. The reason is all blood vessels and nerves will come from the body or the jaw, what you call it as the jaws, into this tooth through this root. Therefore, while uh, applying that force, you have to see that the movement of the teeth should not disturb the root of the tooth. So that is going to be so important. So it has been designed. The lot of forces have been applied to the dental wires with the various mechanics. Here it is, the lot of things is involved in. If you look at the various arrangement, usually that we have not seen because it is put inside the mouth. Usually we want to see, what are the elements that are used to create a force on teeth. So only that we see the front part of it. If you look at that inside that mouth, the small spring that has been used to uplift and give a sufficient force to see that the tooth is coming up using the spring. And also you will see that a wire that has been fixed plugged into another key, which that force is being created by rotating that wire, so that a lot of force will be generated, and it will draw the, or it will pull the set of teeth back. That's what I have seen. This is going to be a different technique. Here what they do is they give the different rotations and hook. Therefore, whatever the extension that has been occurred, that will pull up. And also you will see that a lot of the arrangements have been made through the spring to pull the teeth set back through the arch wires that I will see. There are the various mechanisms. Even instead of this metallic wire, sometimes they use rubber or the elastomers. That is, it looks like a band, rubber band. Just they'll pull it out through the hook that is been provided here to this. Instead of metal, sometimes they use the plastic ribbons also. You will see that here and here. Now, sometimes depend on the situation, crossed also. It means instead of this wire will go up and this wire will come down. That depends on how much force that is required to that. They'll make a suitable arrangement to this. Now, sometimes it is not possible to put that arch wires inside the mouth because of that various reasons. Then such forces will be developed exterior that mouth. So that headgear has been used and the different links. So it is going to be a kind of a looks like spring. So what they do is just they'll shift the anchor to the different positions of this hole, so that the force will be created externally to that. See, a lot of things, a lot of arrangements and devices have been developed in the case of the dentistry. There are a lot of mechanical devices are available to correct the arch of the dentistry. If you look at this arrangement, it is going to be very interesting. This is going to be, if you look at the outer structure, and here it is been the length or the distance between the two, it is going to be very, very small. Usually we call the upper jaw or the maxillary portion in the case of that dentistry. To correct the tooth position, it is only that possible to enlarge the palate gradually over time. So what they do is that fix this attachment to the entire these teeth, and there is a small hole in it. So in this case, they'll insert a key, and if they rotate it, so what happens, these wires inside that, it will expands. When it expands, it exert the force on the either side, right? Just you observe the position of the locate that is here and that here has been be expanded. It means that wire along with that it has been pulled away, so that it exerts a lot of force on these jug, and gradually they'll move apart. Just you compare the distance from here to here, and after the surgery that is going to be here to here. So here the design of these arrangement needs the support of mechanical engineers in creating the tension, amount of the tensions that is required, and how much turn it has to be rotated, the design of the screws, and all everything is a part of mechanical engineering. So this what exactly, if you look at this style, it is a palatal, the bone expander. It means here, not the tooth as if that has been moved in the part of the palatal bone has been moved. So in the end of the session, I will take the other part of it. Instead of, this is a very gradual force, it takes something like about 2 to 3 hours. But nowadays it is possible to manage within a few months how to make it. It is called rapid maxillary expansion. So this is a very slow. In rapid maxillary expansion, it is going to be very rapid. So these type of palatal expanders are being used for the adult, likely something we call it as 15 years and above. If it has been well below that rapid maxillary expansion, it is going to be very helpful. So different techniques and methods are being used to move the palate that is being observed in it. The bonds and structures, it is going to be interesting. Sorry for the interruption. Let us go through something details about the bones and structures. Bones are living tissues, we all know well, and blood vessels that carry the lot of major activities that happens in the body. Particularly the case of the dynamics, the role of bones is going to be very prominent and going to be very important. The structure enables them to grow. They transform and repair themselves throughout the life. So once the part of bone is worn out, and that you will see that it heals up and then repair themselves, it is going to be an automatic process that happens throughout the life. At the beginning, usually we born with more number of soft bones. There will be 300 soft bones. During childhood and adolescence, that cartilage grows and is slowly replaced by the hard bone. It means as we grow, that bone will become that harder, and also that union takes place between the few of that bones. And some of the bones are fuse themselves and resulting in adult skeletons about 206 bones in general. Generally that you will see from 300 bones to 206 bones. It has been reduced as we grow. There are two types of tissues. The one is a compact bone that is also known as a cortical bone. If you look at that outer the part of it, it's in this case I have taken a bone example having sufficient thick, and most of the time the cortical bone have a very small the thickness. it is going to be very hard and dense. Usually it takes a lot of load from the compact bone. Where the cancellous bone or spongy bone or trabecular bone, it is the inner layer of the network. It is lighter. It is less dense than the cortical bone. So it is true that when where the blood vessels or nerves that pass through, it makes a kind of a provision to fill with this fluid that helps a lot. That will be discussed in different chapters. So here that cortical bone is a very strong, and that structure as has been shown here. It is microscopic view of that. The spongy bone has a very less strength compared to compact cortical bone. See, for example, most of the straight bones, they look straight, but in fact, always there will be a kind of whatever the force transmit through bone, it is not the straight, but they are little different. They are away from the axis. The nature has made such a way that when the force is away from that axis, instead of member subjected to the compression, it also takes a kind of a bending moment. I hope you recall in the machine design, when the load is being applied along that axis, our conventional formula for stress, load by area holds good. When the force is away from its center of gravity or the CJ or the axis of that, it develops bending, right? That bending moment is equal to force into that eccentricity or the distance of the force from the axis is being considered. Not only tensile or axial force will be present, also bending moment are also present, that is equal to force into distance, that is P into E. Therefore, in case of bones, you will see that they are not straight, looks like straight, but loads are applied at a different axis. Therefore, it is become like a beam. When you look at the structure of a beam, the core or the center of the beam experience less stress. Even in case of torsion, you will see that the stresses are very less at the axis of the shaft. Either twist or a moment, that you will see that the mid of the beam takes less load, obviously lesser stress. Therefore, bones are also made such a way that they are not purely subjected to kind of axial stresses, but they are also bending, twist, that also being taken place. Even you consider the location and ideally how the tools has been taken, it has been going to be very interesting. If you look at how our teeth have been arranged, it looks like at the tip they are being intact, but the roots are at different directions. Those directions will create a kind of the bending in the tooth. That's why you look at, if you consider a single tooth, at the outer case that you will see that cortical bone, and the upper case is the hard the tissue. And if you go to the inner part of it, it is going to be a soft, and the mid is going to be a little hollow. The root canal treatment, that when it is been insert into the teeth, that is through the soft one. Therefore, every tooth has a spongy and very soft tissue at the mid of the teeth, where it supports a lot of nerves and blood vessels in the teeth. So it is going to be quite natural. Now, there are the two types of bone structures. One is the woven bone. It is characterized by the haphazard organization of the collagen fibers and is mechanically weak. The lamellar bone, it is characterized by a regular parallel alignment of the collagen into the sheets, what that has been shown here, and is mechanically strong. The most of the bones, long bones, it may be thigh or the leg or the hand or whatever the structures that we have seen, They are the lamellar bone. They have a very strong. What are the woven bone? Now, woven bones have been grown very fast, where the area not exposed to not much load are the stresses. This type of the woven bone can be seen when the fracture occurs. Any bone that fracture that it occurs, it is separated by a distance. The beginning, that bone grows in between the two fractured surfaces, right? That bone that has been grown in the absence of any day-to-day activity forces on it. Therefore, that you will see that a soft bone grown between the two fractured bones, it is very soft and indoor. When it is being exposed, they'll arrange themselves and it is going to be part of that. So that's why in the most of cases we feel that, and also we experience that bone, once it is fractured, we never get the same, what you call it as the strength of the bone after the fracture. Because whatever the bone that has been developed to heal it, thereof the woven in the bone tissues usually do not have much strength of the original bone that it has. I hope that as a mechanical part of that, usually we talk about the Young's modulus and strength of bone and the different materials to understand and compare what you call it, their strengths. Ultimate strength of the bone will reveal how much load that it can bear. The strength is a capacity of the bone, and it is for the cortical bone that you will see that compression is higher than tension. Because most of the bones are always subjected to kind of a compression, and very rare the subjects, bone are subjected to the kind of a tension. It is some part of dental that we see when the forces being act, which they'll act like a kind of a beam. Some part of the beam will either below or above, depend on the location of that force, will be subjected to the tension. Therefore, if you look at the values of the compression is more than compared to the tension, and even if you compare it to the shear, it is going to be very small. So the whatever the values that have been given, it is for a dry bone. Say generally the dry bones values are being set and accepted to be very closer to the living bones. It is difficult to conduct the experiments on the living bone. Therefore, the experiments on the dry bones, it is going to be more valid and very agreeable. If you look at the Young's modulus, so that will gives you and how the bone deforms. Laterally, it is going to be very important because the most of the bone structures facilitate nerves and the blood vessels. So any contractions of that bone on the other side will squeeze the blood vessels or the nerve system. Therefore, it has to be very important, the values of that Young's modulus and the Poisson's ratio. It is going to be very important. If you can compare the general, we use the stainless steel for implants and titanium. It has half of the steel, it is a titanium. If you look at that cortical bone, good bone, its value is very small, it is going to be 21. So it is almost to say around 20, if you call it, it is 20% of the titanium. And cancellous bone, it is very, very small, and the cement used for a repair kind of thing. So it is going to be around 2.5 to 3.5. That is going to be the values of this. Then very interesting part of it is, in case of a fracture, the people use an implant of titanium or the stainless steel. Suppose when bone is broken into two, then a stainless steel or the titanium rods are being inserted in. They'll allow to heal up then later on they will take it out. Always that question arises, is it necessary to take that implant or the wires and put it in that bone after that? Certainly it is very much essential. What it says, that is medically, whatever the forces comes from the upper part of fractured bone will pass through metallic implant or the wire through that, and it will passes. It means at fractured surface, all the forces are transmitted via implant. Therefore, that the bone surrounding will become weaker and weaker because it has no function to transfer the load. All loads will be transferred by the implant. Therefore, gradually the bones will become weaker. So it is when the bones have been healed up, it is necessary to take out such wires or the implants from the body. It is almost been visible. Usually medical practitioners will decide when it has to be taken out. So usually to understand the behavior of that bones, usually we do tensile test. It is going to be more appropriate to understand the strength of it. This is a typical stress strain curve for bones. You will see that there are the two curves, and it is blue one, it is refers to the compression, whereas in the case of it is going to be for a tension. If you look at the yield points for these two, and being referred to as ultimate, that is here, so it is going to be around the 200, where in the case of tension, it is going to be nearly likely being the values of 115 or the 120 that is being taken. If you compare these two, we are not interested in the post-yield region because loads have been applied such a way that it is going to be a very small and not even 10% of it. Obviously, if you compare the behavior of the bone, compression takes the maximum ultimate compared to the tension. So it is from the interest of engineering point of interest, what will be the yield point when it is, what do you call it as, the strain rate is going to be 0.2%, what happens to it? So this is a something like offset method to determine the yield point, right? Generally in practice, so that is going to be this. If you look at the values of that, so here the values of elastic modulus or the strengths or the strain that changes from bone to bone. It is not like even percent to percent that value that changes. So it is not like our engineering materials. Most of the behavior is similar, but in this case, it is very difficult. Usually, they have a wide range of the values. If you look at any articles, that is going to be usually a wide range that usually been addressed to that. That elastic modulus, it is going to be around 18 gigapascal compared to 200 gigapascal for steam, and the tensile yield stress has been around. And if you look at that, strain rate is going to be 0.67, that comes to be around here. And also the compressive, what you call as the yield stress, that is been taken to be here. It has been the higher value of 205, and strain it is going to be more than 1%, 1.3%. And similarly, that shear modulus that has been computed from the values of Young's modulus and the Poisson's ratio of the material. So usually the high value of the Poisson's ratio have been taken in calculating the shear modulus. So whatever the expressions we use it in general engineering mechanics will be used here to calculate the shear yield as well as the modulus. So this plot, it shows for a cortical bone, a good bone, or the hard bone, whatever you call it, that has been the stress strain curve is shown for this material. And also this graph, it is shown for a soft tissue, that you will see that elastic modulus, it is very, very small value. It is here, it is going to be around 18,000. that you will see it is very, very small, and the values of the stresses are, it's totally, it will not take any load literally in every day-to-day life. Okay, then if you take that in earlier, what these all values are being taken along axis of the bone. It means along the length of the bone. And the properties are different when the loads are being applied normal to that, because most of bones are likely collagenous and laminar and being grown in the direction of the axis. Therefore, obviously, they are weak in the other direction. You call it as properties will change with the direction, right? Anisotropic materials that you can call it. Okay, fine. If you look at that values compared to compressive, it is almost like not even 50% of it that it takes. It is going to be very weak in the lateral directions. Okay, so these graphs are going to be very, very important to analyze. So while I'm giving this a lot of information about when the load has been applied along the axis or even the transverse direction perpendicular to this or even the shear, because while modeling with the finite element, you may need a lot of data, directional the stress data that has been recorded. It is going to be very helpful in the finite element analysis. Various types of joints have been seen in our body. There are the three types of joints that usually we classify. One is immovable or fixed joints, fibrous joints that have been referred to as that found in the cranium. In the cranium means in the head, there's a lot of sutures over the head, but they will not move. But there is a joint, we call it sutures, right? So they will not move. In the case of the pelvis and the long vertebral or the backbone, it has been fixed to that, but it will not move. That is the pelvis and the backbone, it has been fixed via fibrous material, but there will not be any movement. So it has been totally, it's a kind of bone that I will see. And slightly movable joint. It means very, very small, so that the rotation is not more than or around 12 degrees on either side. That you will feel. Vertebrae or the backbone, they will not rotate fully. Only the part of they will rotate. And there are freely movable joint. They called synovial. It is in the presence of synovial liquids and all. The movement, it has been more than sometimes 40 to 60 degrees, then been referred to as movable joint. Again, these mobile joints being categorized with the ball and socket, that is the hip joint, the hinge joint, the pivot joint, gliding joint, or a saddle joint, or condylite joints, all the structures that have been shown here. Here, in the case of the saddle and the gliding, you will see that these joints, when the joints also can move, push away, they move from others, so it will glides, right? And also can be a saddle. It has been bent. Here it is going to be very limited. It is going to be slightly limited, the cartilaginous bones that you will see. It is a kind of thing. And freely movable synovial joints, or it's going to be referred to knee joint or in this ankle joints, right? And the hip joint that you will see, these all comes under this type of the joints in this. How the joints are being made with? There are three types of the connective tissues used within the joint for a successful and constrained, what you call it, constrained joints. Cartilages are very common. They form a kind of a cushion between the bone in order to stop them rubbing. Usually that cartilage looks like a white spongy kind of thing that you will see at the end of the bone. So it is a one bone, right, in the upper. And here you will see this, that layer, a thick layer, the material, a soft material, it is being referred to as the cartilage. And another similar cartilage for the bone, that you will see that the cartilage that has been fixed here. Cartilages are found at the end of bone. They'll give you kind of a cushion when they come in contact with, right? Okay, that's fine. The ligaments are the very strong strings that holds the bone together. It means the upper bone and the lower bone, he will see that ligaments are being crossed like this. They'll connect from here to here in the mid of this. If you look at the cross section of that any bone, that you will see ligaments are like threads or strings that holds the joint. So usually a lot of forces are taken by these strings to see that joint is intact. Even when you give the moment, it rotates and deforms. So in that, see that the ligaments are also being expands and holds the joint intact. The tendons usually, whenever that muscle acts to contract or to twist or to rotate or move that joint, by the activities of that muscles, where the tendons are attached to the muscles to the bone, that is help in applying the force to the forces to the bone, so that the joint or the movement that it occurs. So within joint, that you will see that the cartilages and ligaments plays a very important role, and any liquid or the membrane that it contains within this, it will separate the bone in contact. Therefore, there will be no physical contact of different bones, other jointery bones in this joint. Okay, the most of the joint failures that it occurs due to deficiencies or the defects, or it may be trauma or by the accidental, some part of it will be get damaged. Then if you first affecting the part is going to be a liquid, otherwise it is going to be what you call it as the soft cartilage bones. The cartilages are being especially made soft, like they are different from all other living tissues. The reason is cartilage will not grow or repair themselves. Once it is get damaged, the damage is in a permanent. It won't repair itself. There won't no question of healing it, because they do not having any living tissues inside. They do not take a support of any blood or nervous system within this. It looks like a very spongy material. It absorbs a lot of fluids from that. During action, it squeezes or compresses, then it oozes out all the liquid within that from the cartilage. When it is relaxed, you will see that it like a sponge. When it has been come to that, it takes the fluid from slender membrane towards in that. So kind of a pumping action that is it takes place. Therefore, all the nutrients will be taken during action. It means while you are walking, you will see that bones are get compressed, then also be cartilage. Cartilage compresses, then all the fluid, right, that goes out of the joint. And then when it is being relaxed, they will enter. Like kind of a pumping action that is takes place. Most of the cartilages are being survived with this mechanism. So that's why any scratch or something like happens to the cartilage, no question of repair themselves. Only you have to suffer to it. Otherwise, you have to attend the medical attentions that is very much required to this. In the study, we have taken a lot of work on development of the cartilage tissues. A couple of my research scholars have successfully developed a material that one can replace the living cartilage, damaged living cartilage with a new fresh composite. Recently, two research works been going on and been published in that. I will take a few slides from this. The first paper has been published in Nature Scientific Reports, that is nano hydroxyapatite reinforced chitosan composite hydrogels with the tunable mechanical and biological properties for the cartilage regeneration. And similar work, basic work have been published in Material Research Express and also in the conference proceedings of American Institute of Physics also been produced in this. He was the first research scholar working on some of the biomaterial tissues or the ceramics that can be used for the joint purpose. Now, this paper, if you look at the title, it is composite has a tunable mechanical and biological properties. It means mechanical properties of the composites will vary according to the requirement at instantaneously. It has been more interesting, the values of what you call mechanical properties that can be changed, and also biological properties are also being changed accordingly. It well matches with the cartilage regeneration. And also it is very interesting is it is something regeneration means when the composite fails by number of pieces, it will reunion itself. It means composite will grow itself to reunion and it works in continuous to this. So it's a kind of work that has been taken to this. I will take the few slides how the things has been taken to that. So this is going to be the structure of the mid. It will give you a picture of the knee joint. Here you will see that is going to be a cartilage and all other that the ligaments that has been taken out, and also what exactly that articular cartilage that you will see, and the upper part of it is completely being covered, and also the lot of that ligaments that I've been told. So these ligaments will hold the joint intact, and it is going to be tuber. It is the bottom portion of the. So any damage that is been occurred for the cartilage, it is amounts to this. It is going to be how we are going to replace with that. This picture will give you the clear picture how the cartilage looks like in the joint. It works like a shock absorber, and also it is a friction-free surface that is being taken by solenoid fluid in between the two parts of it. So there could be damage on the cartilages. It may be because of the injury or osteoporosis. A lot of that issues will make it, but this type of disease is going to be very common for the people or the 50 years or be about this. There will be a lot of treatments are also being available. The rough cartilage will be trimmed and be grinded to see that it is going to be the softens. Or sometimes what they do is they'll insert a lot of what you call it as the pins inside of that. They put small up the holes and it will be in a refill. That also the people will do that. So that is going to be the structure of pipette, how the surface, and it will show that. Suppose if you want to replace the cartilage, what will be the alternate in the case? That is being discussed later in this. So when the surgery fails, that you will see that how that it happens. That is the entire that joint will become reddish and swallow once it has been opened. If it looks like this, so this is the artificial knee joint that has been put it in. That will be the picture of this. There are some of the interesting points to mechanical engineers. That is how knee joint is being loaded. Just you look at the various activities, something like cycling, and the rotation is going to be, the joint is 60 to 100, and the load takes about 1.2 times. I'm talking about each joint, two legs, the two joint. I'm talking about each leg or each joint it takes the load about 1.2 times the body. Suppose if you are weighing the 50 kg, we'll see that around 60 kg that has been taken to that. While walking, each leg joint will take the force 3 times. It means if you are weighing 150, it will take you the load of 150. And also in the case, if you use a staircase downward and the upward, that you will see the different loads that have been taken up. When this squat rise, half squat, when you rest it, if you see that interestingly, each joint will take you the 5 times the load. It means around 250 kg of force will come on the joint. When squat, you've done it severely, even it can go up to 7 times. Each joint will suffer a huge load that is equal to 7 times. So these are the data that are being taken out from the scientifically from the use of EMG's activities that has been taken out. So usually all our designs will be based on the highest value for 7 times, but will not suggest for any such severe exercises too. So from this, it is very clear that each joint will take you up to a load 7 times the body weight. So it's also interesting to see that when you, while walking, one of the leg leaves off that ground, then the entire body stands on the one leg, right? But whole entire body weight will comes through the joint, and also the body weight will act at the CG, and also there will be bending also. Therefore, not only a compressive load, but also bending, heavy bending load comes to the joint. What are the substitutive materials for the cartilage? One of the theses submitted by the Kamal Babu has done a lot of work on cartilage materials, and he developed polyvinyl alcohol hydrogels, a promising material that is reinforced with bioceramic, that is a tricalcium phosphate. This ceramic has been developed by processing cuttle bone fish. That fish bone that has been taken into the processing. This material have been used in the PVA hydrogel to prepare that composites, and a lot of experiments reveals that it is going to be more useful. The objectives of that work is to synthesis TNTs from the titanium oxide nanoparticles. A lot of additives have been made to that to prepare that composite. So in the brief, that these are all the articles published in Nature Journal. You can go through this. How to synthesis titanium oxides nanotubes for a use of developing the composites that can be seen here are the different structures that has been addressed here. How what are called nano reinforced materials have been developed. Now, this is a piece of that hydrogel. It looks like the very the transparent, and when you hold it in the finger, when you press it, you will see that it compresses to an extent so small. It means it won't rupture, it won't break. But even the 10 mm thick cylinder can be compressed to 1 millimeter or even less. So it is so spongy material. If you look at the structure in the right side, the different what you call the combination of the reinforcement and hydroxyapatite, how do they behave? And if you look at the formation of the material, how the spongily that has been taken into these pictures. Okay, it is cartilage. I will not go into the detail. The lot of polymers are available for the reinforcement, and in the among this we have taken up this hydrogel and the PVA, and for the reinforcement hydroxyapatite that has been taken, that is been referred to as what you call as a bioceramic. So the objective of the project is to develop a material which can be used as a substitute for the cartilage material. So that you will see that how that material looks. It is going to be how that hydroxyapatite reinforced material, it has been derived from the fish bone, and it is been crushed and again calcinated at 800 degrees centigrade for more than 6 hours and whatever the material that has been processed chemically that has been used as a reinforcement. That you will see that a lot of hypothesis that has been taken in the technical support of XRDs, TAs, all the things that has been done systematically, and also that is the material that has been taken out. This is going to be among all the materials being developed, the best composite made hydrogel being developed with the structures compared to the previous one. Okay, what is the swelling and the wettability of the composite? Because cartilages are being particularly made to absorb the liquid from the surrounding. Therefore, that the swelling ratio, how much that what it that been absorbs, it should be more than 400%. It means if it is 100 millimeters, if you take it, it has to take 4 times of that liquid. It has to absorb so much of liquid. It has to absorb. So these experiments reveals that the HAP with the higher percentage will absorbs the higher percentage, even it will reach us up to 6 times. That is 600 times of that water that it can absorb to it. So these are all the different properties of that. From the mechanical engineering point of view, how this hydrogel behaves with the different proportions of the reinforcement that is being taken here to determine the strength of this. So here that the strength maximum that it goes to be around 1.2 megapascal. But most of the cartilages are subjected to cyclic in loading. It means when it has been told while you're walking or sitting and all the activities, load is being applied and then being relaxed. It is a kind of what you call it as a fatigue. Therefore, how that material behaves in case of that fatigue, because it is a highly viscoelastic material, therefore you cannot expect the loading and unloading pattern will be similar. It behaves in a different way. The second graphs will show when the load is the cyclic, how it is being deformed. Okay, then in the things that has come to the rheological, okay, these are all the various studies, viscoelastic properties have been taken out. And also, if you take the friction test, it is going to be very amazing. So, natural cartilage has a coefficient of friction that is so small, it has been addressed as we do not have any equipment to measure the coefficient of friction. So it is by only the other method of the rubbing material against the another cartilage material at the higher speed, looking at how much the frictions that has been developed, from that only it is being assessed. The reason is coefficient of friction is so small, is 1/100th of friction of a coefficient when a wet ice slides on the another wet slide, right? When ice cube slides over another wet ice block, what is the coefficient of friction that it addresses? It is negligible. So, but the cartilages have 1/100th of such coefficient of friction. It is so smooth, perfectly smooth that you can call it. So these are all microbiological studies to proven to say that the material is biocompatible, so that it can be used in the body to that. The another work, I hope if the time permits, okay, I have 1 minute left. So anyway, just in a glance that I will make it, one of the good work is done the long back. It is published in Angel Anthropoetics. It was a work is done at Bapuji, the college, dental college at Davangere, when I was working at BIT Davangere. So it was one piece of work that has been taken to. Now this is to understand the exactly is. I have shown you this slide has been a long back in the case of the palatal expander. It is a very slow process. In the case of a rapid maxillary expansion, right? In the case of rapid maxillary expansion, that it is widened such a way that it will create a complete the fracture on the palate, right? It will split into two and it widens about 5 millimeters, right? So it at the mid of this palate, it will separate this bone, and this bone is slit into two by applying that force, it comes to around 5 millimeter. What happened to the structure of that element? What happens to the skull? What are the net effect on that? It has been studied. That the inferior parts of thoracoid plates were markedly displaced laterally. These are all the medical terms that has been used. And when the plates are being moved by 5 millimeter, then there will be a displacement, vertical displacement in the palate levet will come down, and it very badly affect the anteferonier border of the nasal spectrum. It means above that, and also in the vertical plane, you will see that there will be a lot of difference in the osteostructure. It is the bone structure that it makes a difference. It means applying the enormous the force on the palate, that mouth, it affects the other part of the head also. That is the purpose of this study. It has been done, taken the CT scan of a dried bone in that skull, and various points, that is radio opaque materials, have been pasted to trace the location of the slice. From that, a lot of the points that has been marked, even though if you take the X-ray, that these particles will be a reference point. When you take that CD of that, we will see that different slices have been taken in the entire skull, and the boundary of that bone, that and that thickness. No, one line has been traced from here to here completely, and also inner to, so that the lines have been created, so that three-dimensional finite element body has been created using CT scan. So this is a three-dimensional model of skull. This work has been done approximately 15, 16 years back. Looking at the capacity of the computer or this finite element packages are being so limited. In spite of that, the work has been done. Around 16 lakh nodes have been worked out to develop the structure. If you look at just you observe the mid plane of this, and here is going to be the palate. The details of the palate has been also been built up, and this bone is being separated by 5 millimeters apart from that. Okay, then when it is being displaced, that has been moved about 5 millimeters, what happens to the eyeball locations and also the ear and also zygomatic arch? That has been observed in this. So this is the finite element result. The final result I am showing it. Maximum stress that you will see interesting, it is going to be 57. So at the where it has been separated on the palate suffers a lot of stress, and also that you will see that the lot of region, even in the region of the sinuses as well as in the above, and also even well below the behind the ear also been get affected. So entirely that you will see nearly to see that 50% of that head have been affected with the surgical procedure. So it is going to be very effective. And also the results reveal that whatever the stress concentration points are being observed on that skull, it well matches with the complaints of patients where they are having a severe pain. The pain is not at where exactly they done the surgery, but the pains have been observed at other places than the surgery. Therefore, the compliance of the patient and the finite element work that has been well matches with it. A lot of data have been taken out. What are the von Mises stresses in the different part of stress? And also you look at that internecial where the surgeries have been done at this location, maximum stress that has been, and also even that zygomatical and that frontal, even though it is far from the surgical place, you will see that the stresses are also being very higher. So it will indicate that the study, the displacement, there will be a lot of movement and the sutures have been done that will be resulting in the stress concentration. That's why the patient feel the lot of the stresses and the pain other than the surgery. So what exactly that entire paper reveals that it is going to be very interesting. But as a conclusion, it has been drawn with the results of the the present study using three-dimensional FEM skull indicated that the transverse orthopedic forces not only produce the expansive force at intramaxillary sutures, not at exactly that entire that the maxillary sutures will be get affected. High forces and structures on the craniofacial structure, the complex. It means the front face and particularly cygnoid and zygomatic. It is just above the level of air also been affected. So it was the total conclusion that has been done with this. Okay. I hope that I've taken about 5 minutes more, the last case example. And a lot of work is going on with developing a material for the cartilage and also to analyze this. So from this, it is role of a mechanical engineer in biomedical, it is going to be very important. Not only developing the processes or implants, but also substitutive material for this human being to tackle the trauma or accidental cases to us. With this, I thank for the invitation to deliver this lecture in this faculty development program, and thankful to Professor Basraj, principal, CIT, and Professor Timaya, and the head of the department, Professor Gnanesh, who is the program convener. Thanks to CIT for facilitating this event, and thank you all for the patience hearing. Thank you all.
Thank you, sir. It was a very interesting and productive session. In fact, we have a couple of questions from our participants. Sir, a participant called Dr. M.L. Mahadevan, he is asking that how to correlate the simulation results with the actual feedback from the patient or patient. In fact, if the Dr. M.L. Mahadevan, if he is online, can you just unmute yourself and ask your question?
Dr. Madhivan, please.
I'm unable to hear.
During the simulation, where we have certain assumptions and we are making it up, sir. And while in the actual there may be a certain deviation, how far we can accommodate those feedbacks, sir?
Will you repeat the question, please?
Because in a simulation, where we have certain assumptions with load and other things, and while implant the whatever the things, the product with the patients, where we have certain feedbacks from the patient. Is there any deviation? How we can accommodate that one in the further the what is that experimentation, sir?
And see, the simulation work, it is very difficult in biomedical because the structure and all other things will vary from person to person. Whatever the simulation that we are done it is true for the what example of the slides that we are taken, it is true for them. But most of the cases are being observed that complaints are similar. Suppose if you take about some 25 patients, if they have a very similar complaint, that means something is happening in common. So those things will only be considered, but not any individual. It's a feedback taken by the group of patients, not an individual.
Okay. So there is one more question from Dr. Vasanta Kumar. Vasant Kumar, sir, if you are online, can just unmute yourself and ask your question.
Good afternoon, sir.
Yeah, good afternoon.
Sir, the session what you delivered, it is very informative and excellent.
Thank you. Thank you.
And it's latest topics you covered. Sir, some metallic implants, which is affecting to the damage, especially in the cardiovascular applications. So can I know some alternate materials, sir, like polymer based?
See, nowadays still stainless steel and titanium metal matrix, it is going fine with. But polymer composites are being addressed where they need a very short replacement. So because of high mobility property of this polymer, many usually will support the hard tissues like bone. So other for a soft tissues, it has been fine. Metal matrix are the composites. Nowadays, the lot of materials, range of materials are available for replacing the tissues.
Participants, if you have any more questions, you can just unmute yourself and ask the question. Okay, I guess there are no more questions. So I'll just wind up the session.
Okay, thank you. Thank you all.
Okay. I request all the participants to give the feedback of the session. The link of the same is shared in the chat box and also in the WhatsApp group. Okay, we are at the end of this second session of the 6 days online national level FDP on recent developments in mechanical engineering. I'd like to thank Dr. G.C. Mohan Kumar, Professor, NITK Surathkal, who in spite of his busy schedule accepted our invitation and engaged this session and shared a lot of information on the mechanical engineering applications in biomedical field. So thank you so much, sir. Thank you so much for your, all the inputs. Thank you, sir.
Thank you.
Thank you, Dr. Mohan Kumar, sir.
Okay, thank you all the participants for joining the session. We'll be back with the next session at 3 p.m. by Dr. Veerabhadrappa Algur, Professor Rahu Bahadur Y. Mahabaleshwarappa Engineering College, Ballari. So signing off for now. Thank you. Thank you one and all.
Thank you.
Talk to you. Thanks,